several different areas or several different disciplines, their definitions can be a little bit different. But in soil and rock dynamics, that is the definition of pseudo velocity, PSP, pseudo velocity. Same thing for pseudo displacement. Okay. This one may be correct, may not be correct, and many times this one is not really exactly correct velocity, but this one should be close, okay, close to the real velocity, but that is still pseudo, I'm sorry, it may be close to the real deformation or distance, but there is still pseudo displacement. And particle velocity and propagation velocity. Again, the best thing about the particle velocity is this one. You have the you threw a stone in the pond, and it will cause those circular waveform, and those circular waves will propagate to the coast of the pond. But when you have a small ball somewhere in the middle of the pond, that ball will usually move up and down. That ball will not come to the shorelines. Okay. So motion of the ball is called particle velocity. But we can actually see the waveform propagate, right? So that propagation velocity is the phase velocity. Okay. Make sense? It's the phase velocity. Then another one was, what was the last one?
Propagation phase, which are the same.
Propagation velocity is exactly the same as the phase velocity.
And then particle and pseudo.
Yeah, particle and pseudo is something that we explained.
Mm-hmm.
Did I say group velocity in there?
Yeah.
Okay. Group velocity is also the popular word, but in soils and rock dynamics, we don't have to consider anything about the group velocity. So that's the reason why I dropped it, because it may cause another confusion. And you may wonder, when we have compressional wave, okay, compressional wave, what is the particle velocity? Think of that. When we have compressional wave, what is the particle velocity?
You're talking about the direction?
It's zero, it's not.
It's going to be more, I mean, particle velocity will be moving this way. So,
That's right. Okay. Can you guys sit a little bit come together? Shoulder by shoulder. Okay. I will apply. Okay, you two guys are the physical model right now. Okay. Okay. I will apply some impact load. It will cause some propagation of the wave. Okay. This time, look at this one. Okay. Look at the contact surface between my palm and his shoulder. You felt the something was transferred to you, right? Okay. At the moment that I pushed him, then probably he pushed him. That is the propagation of the wave.
it's like the dropping of the ball. You know, those little metal balls.
Yeah, yeah. But okay, again, there is a propagation velocity. Then when I push him and release it, then a particle in here moved this way and came back, right? That is the particle velocity. This particle velocity really related to the amplitude of the vibration. Propagation wave really related to the material properties of your bone, your muscles, or whatever. Okay? I guess other than that, most of you did it all right. Actually, the Garrett wrote down the definition of those four velocities with his own language, and it was really great. Okay. I know some of you got the materials from Wikipedia. You mentioned Wikipedia. Some of you did not mention Wikipedia. It's always good to mention the source of your information. Just one comment to Wikipedia is really a great source. I also use the Wikipedia a lot of times. But don't believe too much, or I should say, do not believe in Wikipedia. That's the free information, right? Free information times time is wrong, and nobody is really responsible about those free information. And again, when you look for the information in the web or Wikipedia or whatever, always have this one in your mind. For the same terminology, even for the same terminology, the definition can be different depending on which disciplines they are in. Okay. So what I found from probably you guys answer for those definition of the wave, I felt like the definitions are for some different areas, not really soil and rock dynamics. Okay.
Sorry, Eric.
Get a little bit left that you just turned it. If you turn it this way and this way quite quickly, and he will have the motion sickness. Lesson, what is the lesson number?
17.
17. Foundation isolation. Okay. Foundation isolation. Objectives. If vibration caused by vibration source is too high, then we need to design foundation isolation. If you are a billionaire, you don't have to learn this one, you don't have to know this one. Then you just call a guy who knows how to design the foundation isolation. But the fact is, we are not the none of us is the billionaire, and we are the geotechnical engineers. So most probably, we are the one who got to design the foundation isolation. Okay. So we need to know, or we need to understand foundation isolation. Okay. This one is not really good. Let's give some time to Corey so that you don't miss this one.
So what would y'all like for breakfast Thursday morning?
Probably.
Why don't you make us some like pancakes and bacon, and eggs, biscuits, orange
I'm gonna need
juice.
all of that 13 minutes you were late.
We need somebody to be late again, right?
Yeah.
In 20 minutes.
Oh, y'all want donuts or biscuits or
Yeah.
which one? What do you want, Dr. Saul?
I really take the breakfast before I come to school.
Nah.
Well, I can take the just maybe one donut.
Okay. You want chocolate covered?
Yes.
I'll pick them up if you want to give me one. Since I'm right next to
Yeah,
you.
that would be easier since you do pass them.
Actually, the thing is,
Hang on, there's
I
more.
really enjoy this taking donut in the early morning.
I don't know if that's
Jimmy, how many donuts
But-
you want?
oven.
As I take the more and more donut, I figured out it caused some trouble to my stomach.
Yeah, all that sugar.
Maybe sugar, maybe the oil, I don't know what exactly caused the troubles. So nowadays, usually when I eat a donut, maybe one or not anymore. The one from the cold one from Walmart, that's really the worst one.
I can imagine.
Okay.
Welcome back, Corey.
Okay. Again, the Corey will not, maybe a billionaire sometime in next 10 years, but right now you are not a billionaire. You may become a billionaire if you know how to design the foundation isolation. Because not many people knows how to design the isolation. And also another fact is we don't design foundation isolation very frequently. One of the reasons nowadays why foundation isolation is not very popular is nowadays the mechanical people or structural people, they are also very good to isolate their machines or equipment. Okay. So there are actually a couple of different options when we are talking about foundation isolation. So let's think about some options. Again, the machine itself may have bushings, okay? That may properly isolate their machine. One of the good examples for the using rubber bushings so that vibration does not propagate. I should not say it does not propagate, I should say it can reduce the vibration substantially. Is vehicle engines. We know vehicle engines, they vibrate, but when you are in the cabin, you don't feel that much vibrations. The reason is
Engine mounts.
engine mount.
Because of the rubber pads on.
Yeah, typically we have rubber pad for the engine mount and transmission mount. That means those engines transmissions, they are not really directly connected to the body or frames. Okay. So they vibrate, but vibration is limited on those engines and transmissions. Okay. And this kind of technique, we say, that is a kind of active, ACTIV, active isolation. Some vehicle companies, they are very well known to isolate the vibration. What is that company? Huh?
Lexus.
Probably the Lexus. Okay. And again, I'm not a salesperson of Lexus. I don't own any Lexus vehicles. But what I know is their engine mount is not really rubber. It is something like liquid filled whatever something. The inside and the engine mount, it has maybe when they say liquid, it could be some kind of special oil. So their engine or transmissions are kind of floated on the top of some of those liquid. Right? So that it can actually further decrease the vibrations. Okay, something like this one. And another vehicle company nowadays, Hyundai, they are saying that okay, they control the noise and vibration from the source. Okay. You may be surprised. the vibration of compressors nowadays. Think about the window air conditioners. All the window air conditioners, they are very noisy, right? Modern window air conditioners, they are a lot more quiet and they are a lot more energy efficient. Part of the reason is they control the system so that it can have less friction and less vibration. I don't know how they actually reduce the vibration from the source. What I know is they actually redesign the pistons and cylinders, whatever, so that it can cause the less vibrations. All those things are active isolation in terms of machines. This is really the best technique. As far as, if you can reduce the vibration from the source, that is the best and the most economic technique. Then, let's say somebody did his best effort to reduce the vibration from the source, but we know that those vibration machines cannot completely eliminate the vibration. Then it will come to the civil engineers. Okay. Then civil or geotechnical. Vibrations is something like this one. Let's say this one is the ground surface. And we have vibration source. It will cause the vibration. We know that.
Man, did I catch it on camera?
We know that when we have vibration source, it will gradually die out. Okay. But when the distance from the source to, let's say, some structure is close, let's say somewhere here. Let's say our structure is here. And amplitude of the vibration may be still quite severe. Again, when we talk about amplitude of the vibration, that is related to the particle velocity. Okay. Then think about how we can reduce the vibration in here.
Have a medium between it, like around it.
Somewhere in between those two spots, we got to put something, right? And think about the practical technique or practical means that we can put somewhere here and it may effectively cut down the vibration.
Different type of soil.
Different types of soil.
Yeah, maybe a pile.
Pile. Okay, piles are also actually used. Okay, but we will talk about the foundation isolation using piles. So somewhere here, let's say we put some kind of new materials. New materials. So probably what we need to do is, okay, we got to excavate a trench here and fill some kind of materials in the trench. And think about what kind of materials in this trench may be very effective to cut down the vibration. What kind of materials?
Sand.
Sand. Let's think about this way. Before we actually talk about what kind of real materials we may use, think about conceptually, okay, what kind of materials will be will be good to put in there.
Highly elastic.
Highly elastic.
It'll absorb it. It'll absorb the the wave.
This one and this one is a lot more elastic than this one, right?
What about something that'll deflect it?
Okay, let me just talk about Jimmy's comment. Highly elastic, very elastic, very elastic. So we put those highly elastic materials.
Okay, let me rephrase that. I mean, I guess it'd be, I mean, like rubber. I mean, since I'm saying like highly, like, let me see. I say elastic, I guess.
It's elastic, but probably what you meant is
Yeah.
low modulus.
Yeah, low mod, yeah.
And also the Nathan's comment was some kind of different materials. You can think of very rigid materials here too. The point is the material should be, this material should have very different modulus or stiffness than surrounding soils. Why? Let's say you are designing this room soundproof.
If you make it out of the same materials, I mean, it's just defeating the
Let's
purpose.
go to the port.
The further you get away from it, the better.
The further away, I mean from here,
The further away from the material that's already there, the better.
further away means very high, should we have very different K and E, that means just very different materials. But just think about how we can make this room soundproof.
Make the walls thicker, fill the walls up
Make the room thicker,
with something
make
harder
it-
than insulation.
Stiffer.
make it very stiff, and probably we also want to add some kind of mat. So we will combine very stiff materials and very flexible and very soft materials. The whole reason of it should be either very high K or very low K or a combination of high K and low K is if this one is very, very rigid one, this way will be reflected. Correct? Okay, again, think about the wave.
You like hitting bedrock. I have to come back.
Yeah, then it will hit this one, and most of the wave energy will be reflected. Let's say, now this one is the soil, this one is almost the hollow space. Wave will propagate this way. Wave will be reflected too. How?
It's an air void.
Mm.
In a sense.
Okay.
And it hits a different layer, I mean, doesn't it reflect in a different way? Or refract?
It will be reflected different way, but it will be reflected. Whenever there is the big modulus contrast or a spring constant contrast, wave will be reflected. But in those two cases, reflection mode will be different. Okay. Who is good? Very good in running, I guess. Corey is
Jimmy?
good.
Jimmy is.
It looks like
Oh,
Corey
so-
is really good in running.
Jimmy's got his running shoes on, and Corey's wearing pants. I vote Jimmy.
Okay. Think about that. Jimmy is running this way, and then somewhere here he will turn back. Okay. Then probably he will kick the wall and try to kill the energy along this way and kill the inertia. Then he will try to turn it this way. Then think about the compressive stress he applied to this wall. He should apply a very high compressive stress, then he can come back, right? Then another case is Jimmy is running. Let's say underwater. Now we have water. Running this way, and from here it's just free air. Just think about something like the water wall in the Bible, when the Moses were leading those people from Egypt, and he was escaping. And we know the Moses, whatever miracle, right? We have big water wall here. Jimmy is running this way and try to turn back at this boundary, air, water. When you turn around, can you hit the wall and turn around this way? When you hit the wall, then you will just going out to the air, right?
Depends on the surface area of my shoe.
So if something is here, let's say, something, maybe Corey should be here. Can you be here? Let's say Jimmy is running this way, he got to turn back. And he will pull Corey this way and make a turn, right? Pulling Corey this way means what?
Transfer.
Right? He was running this way, he was pushing the water in this way, now he's pulling the water this way. So when the compressional wave travels to a certain boundary, and on another side, if we have a kind of low modulus material, then reflected wave will be tensile wave. If it's the rigid boundary, then reflected wave, compressional wave will come this way, and reflected wave will be also compressional wave. Okay. That's the only difference. But anyway, when we have very high contrast in modulus between those two materials, then it will cause the substantial reflection of the waves. Okay. Then think about what kind of actual materials we may use here. Actual materials. Gravels. Try to make the a lot higher contrast than the gravels, sand, or whatever.
Steel sheet pile.
Okay, that means just the other end. Okay. This is not very widely used.
But it is used.
I don't know whether this one was ever used or not. First thing is, it may be a little bit too expensive. Usually steel sheet piles are thin, right? Then they may still reflect by the vibration and transmit the vibrations, even though most of the vibrations can be reflected, but when they are subjected to high amplitude of vibrations, then they will still vibrate, and it may transmit the vibrations. Something like the glasses are usually very stiff. It may cut off the vibrations quite effectively, but when you increase the amplitude to a certain limit, it may just break the glasses and vibrations can still propagate. Think about some other materials, and probably we may think of piles. Piles are usually quite messy, right?
Could you do a big, it wouldn't be economical, but you would do a big concrete wall around?
Maybe the concrete wall.
What's a real life example of the source of that wave?
B compression.
So like a blast?
Blast can be the source, but wait a minute. Blast can be a source. Hmm?
A little blind though. I can't see.
Oh, okay.
The camera can't see that.
Blast can be a source, but do we know the location of the blast?
No.
So that is very random, right? If we know that the blast will be a certain point, maybe every day we have a blast that day, then probably we may design the isolation technique. But if we are talking about a kind of terrorist blast, it's not really easy to predict. It's not actually periodic.
Yeah, that's what I'm saying. Like, what real life example would you be designing this for?
Big compressions.
Like what though? Like what would cause them?
Let's say in tunnel hole, they have the, I guess on the other side of the tunnel hole, they have the big compressor room, and compression always cause the vibrations. Also in the, let's say Chicago or New York areas, we have subways. Those also cause the vibrations almost 24 hours.
So are you isolating yourself from them, or are you isolating it from everybody else?
Very good question. We can do it either way and both ways. Maybe it's good time to answer your question because you already asked me that question. If you want to isolate the vibration completely, that means you got to isolate this source completely. Then it will be good to everybody. But let's say you have the subway vibrations. It's the long subway, and you cannot really isolate the vibrations of the subway from the beginning to the end of the line, right? Then probably you may isolate your own structure only. You don't care about your neighbors because it may be too expensive to install this one for the long distance. So in that case, there is a kind of partial isolation. Okay. Isolation of the source itself is also called active isolation. Isolation of our individual structure is called passive isolation. We will talk about both techniques. And let's still think about what kind of materials may be used. How about just the hollow space? We put nothing. Time to time, people try to put the sawdust. And I guess one of you said the concrete wall.
Why not like poorly graded sand?
Poorly graded sand. Okay, our surrounding materials are soils, right? Even though you put the poorly graded sand, modulus contrast may not be as high as those materials. Almost zero modulus. Almost zero modulus. Very high modulus. Okay, again, the concept is you should have either very high modulus or very low modulus.
Fill it with water. If you can build a trench that can hold water.
Okay, castle.
I know, right?
Castle building.
Then probably you need to have the big insurance because somebody may fall there and you may be in trouble.
It's possible.
Okay, water.
Well, the castles are still standing. They got moats around them.
Okay, water is not widely used. Hollow space is not used widely. Why?
It's gonna kill it.
Failures.
Somebody will fill it up eventually, right? Or this guy may be filled up by some, let's say, the big window or some water flow. Sawdust, it may be okay temporarily. After 10 years, then this guy will create big trouble, something like the insect, like termite.
What if you used expanding foam? Just a random idea that just hit me.
You mean something like those magic?
Probably the expanding.
Yeah, the
foams.
expanding foam that they put around, they put it around telephone poles when they the
Yeah, like polyurethane based.
you dig a trench, pour the two mixed part down there, and expands and fills your gap.
I'm watching Dirty Jobs.
You can do that. This one should be. I mean, I never saw people use this one, but it should be a new idea. The reason why people did not use this one is probably this material is available maybe only recently. And probably another problem could be the cost related.
It would be kind of expensive, but not if it's closed cell. You have an open cell foam and a closed cell foam. An open cell can allow water in. Closed cell's not. Closed cells is really expensive. Open cell is not that expensive.
Those closed cells are really, really effective in terms of the sound insulation. But at the same time, I think price is really
Yeah.
maybe quite high. But again, as far as you have some concept that it should be either very high modulus or very low modulus, that should be good enough. Okay?
How about like rubber mats? Not economical, but I mean if it's like an inch thick.
Rubber mat. Yeah, you can say rubber mat. Soft rubber, not the hard
Yeah.
rubber.
I was kind of thinking about that a minute ago with the sheet piles.
You know,
If you had a really thick sheet pile with like aluminum on each side filled with like a silicone filler in the middle, it'd be expensive.
what they've done.
This
in-
one, you got to also think of this one.
Because
I've seen like it's kind of related and not. I saw something on National Geographic where they were designing ballistic material for tanks, and what they did is they essentially took two pieces of corrugated sheet metal and then put a bunch of not a bunch, but they put like some angle in there that was perpendicular to the surface, so when a wave would go in there, it hit the angle and bounce back or bounce away from going in.
Mhm.
So something like that. I don't know. Still expensive.
It's still very expensive.
Very expensive.
It's not just expensive, that technique is very expensive.
Yeah.
It's used for those, I guess, Abrams A1 tank.
Kind of, sort of, not to that level.
Okay, again, for those military devices, people really, we don't really care the cost, right? As far as it can protect our soldiers, taxpayers will pay the tax. Actually, we never knew that whether our tax is used to buy those things or not. But usually people just don't care because it'll just protect this country. But again, this one is again civil engineering issue, and the cost should be within the reasonable range. How much is this one will cost?
Not a lot.
possibly free.
Possibly free. You can just drive your truck to the roof. That I think I saw a lot of mills, timber mills in there. You can drive your trucks there, and maybe you can get the sawdust for free. Bring it back and fill it. Air is free, right? Transportation is also free. Concrete wall, we know it's not very expensive. Water is not expensive, but it may cause some safety issues. Very effective, but it can be expensive. Rubber mat, probably this. I think this one may be as expensive as this one. When you think of the installation, this one may be even more expensive than this one. Okay. But anyway, if you have some idea that this material has very high contrast with the surrounding source, then material can be always used. And then I will talk about active isolation and passive isolation.
Hey Doc, about how deep would that have to go? Would that trench have to go to?
How deep it should be? We will talk about that maybe a little bit later. And when we talk about how to design those things, we will talk about what should be the distance from the source, what should be the depth, what should be the width, those things. Okay. Again, this is the source. Just give some time to Alex so that he does not miss this part of the lecture.
So now, earthquake isolation wouldn't be involved in foundation isolation. I mean, it is, but not in this case.
Usually, earthquake isolation is really difficult because we don't know where the earthquake vibrations come from, right?
No.
It can be just right below our building. Then the only way is we got to just float our building in air. It's not really feasible.
In Taipei 101, they have the huge mass dampener. Yeah.
This solution. Again, nowadays, this technique is also quite well advanced.
See how much this closed cell foam is, or open cell. I mean, no closed is expensive.
S- 1960s and 70s, some foundation isolation was designed. Nowadays, again, isolation of those vibrations to the structure itself or machine itself is also well developed. As far as those let's say you can effectively isolate your structures using rubber pad or whatever, that is actually more economic than designing and building those trenches or whatever. If you have source here and let's say your structure is here, if you install the trench, you can think of install the trench quite close to the source and just surround your source with the trench. Okay? Surround your source with the trench, and we will say distance from the source to the trench is R. Height of the trench is H, and width of the trench we will say W. Okay. And if R, this radial distance is lower than lambda R. In dynamics, what was the lambda stand for? Wavelength. Okay. Then this one is called active isolation. Active isolation means we will try to control the vibration at the source. Okay. Then we don't have to worry about the high amplitude or whatever vibration problem somewhere outside. If R is longer or equal to lambda R, usually that is called passive isolation. And think about when active isolation is effective and when passive isolation is effective. When is this guy is effective? If we know the vibration source clearly, apply this one. clearly known. And then passive isolation is effective when vibration source is not known, or time to time when vibration source is widely distributed. One of the examples of this one is the subway systems.
When they're doing the tunnels underground and they're doing the concrete rings around them, you know,
You mean the rings for tunnels?
yeah,
Mhm.
they serve as reinforcement, but when they secure them, they inject them with that glue or whatever. Does that help anything to do with dampening, or is that just more for securing purposes?
What do you mean by glue?
Well, when they you know how they have the bolts or whatever that they attach them to the surface. They also inject them with something so that so they can't back out. Is that whatever they inject them with serve as a?
Those injections typically called grouting. That is usually designed to reinforce the surrounding soils. It may reduce the vibration a little bit, but not a lot. Also for the those tunnels and subways, nowadays they also have the system that those rail cars in the tunnel has. What do you have for your transportation?
Catapult,
Uh,
GMC, truck.
GMC truck. It has the tires, right? What do you have for your own transportation?
Car.
Which one?
Chrysler.
Oh yeah, you said the Camry. It has tires, right? Tires were made of rubber. Rail cars usually have. Do they have tires?
Still.
Steel wheels. But nowadays, people also using those rubber coatings or rubber strips around those railway cars on the wheels. Not exactly to the tire, just put the rubber paddings around the wheels to reduce the vibrations. Okay. So again, if you can control your vibration from the very source, that is again most effective. But we know that in Chicago and New York, the wheels of those rail cars are just the steel, right? It still generates substantial amount of vibration. Then, if you have your own building, maybe 10 feet from the subway systems, then you may still feel the vibration. Okay. Then we know that this depth of the trench, width of the trench, and this distance will all affect on the performance of our trenches, in addition to the soil properties, right? So we will think about how we can actually design vibration isolation. This one is based on 1968. You can, again, Google Wood 1968 and type vibration isolation. Probably you can find out a lot of materials. And the handout that you have today is based on Wood 1968. And to design those vibration isolation trenches, he defined this one, off.
Like a dog.
This one is amplitude reduction factor. Some people say ARF, some people say AF. I like the AF. Vertical. His initial definition was vertical amplitude, but it does not have to be vertical amplitude. It can be any amplitude. Amplitude of vibration with French. Then divide by vertical amplitude of vibration without French. Think about this number should be what? What's the maximum number of this one? 1. Okay. So this number should be always less than 1. But time to time, this number, it can be a little bit higher than 1. Why? Okay. For the improperly designed trenches, what may happen is, okay, think about this one. We have that door over there. Okay. With the door closed, we can actually talk more easily because actually the sound pressure level with the door closed is a little bit higher. But when we open the door, when we open all those windows, probably we got to talk a little bit louder so that we can communicate each other. Okay. Those doors and windows will behave as some kind of trenches. But those trenches may provide some reflections. When the reflected wave is superimposed to the original wave, some of the waves can be amplified, right? So that's the reason why this number can be a little bit higher than 1 time, 2 times, not always. But when we properly design those windows and doors, that means that it can really effectively lower down the amplitude of our vibration. Something like the zero, it's called zero echo room or zero reflection room. Did you hear about that?
Hope they have one over at that place.
NCPA? In NCPA or recording studios, they usually use zero reflection or zero echo room. No reflections. Then you will feel like, hey, just words, just observe my voice. Then you got to talk actually louder volume to communicate each other. But when you have the reflections, time to time, this one may be a little bit higher than 1. And what we would propose is suggested ARF should be usually lower than 0.25 for proper vibration isolation. That means we got to cut down the peak amplitude somewhere 1/4. Okay. Let's go as as much as we can. And he actually did a lot of experiments. Okay. From his experiment, see handout. Okay. You have the handout that shows this kind of contours, or there. It may look like the eye. Okay. The figure at the top is the one that you have. Maybe it's better to show you here. You have a source at the middle, and you have trenches all around the source. Do you see the trench? Okay. Then he actually tried to install the trench with several different configurations. And for one case, h over lambda is 1.452. Okay. If h over lambda is 1.452, that is what? A little bit deeper trench. Another one is, wait a minute, okay, anyway, he did a lot of tests, and what he figured out is, if we just install the trenches all around the source, those are the amplitude of the vibrations. You can see ARF. Those black lines, black area is the region that has ARF lower than 0.125. That means actually vibration amplitude was cut down significantly, right? Only the 12.5% of vibration was transmitted in those areas. And also there's the dotted area, like it may looks like a sand, but the dotted ones is the area where the ARF is 0.25 to 0.125, also substantially reduced amplitude. And the hatched area is the area that has ARF 0.5 to 0.25. Okay. So you can know actually the amplitude can be cut down by installing those trenches. And then the second figure is the one that trench was installed only 180 degrees, semicircular trench. Okay. Then you can see somewhere in here, the black area, ARF is less than 0.125, very effective vibration screening. And those dotted area is the area where ARF is 0.25 to 0.125. But look at those areas. On the left side and right side, mostly they are hatched area. That means ARF was somewhere 0.5 to 0.25. So those areas has actually much higher amplitude than in this area. So one of his findings is, okay, when we install our trenches 180 degrees, only this area, okay, look at this, only this area is the area that has satisfactory low amplitude. Those areas, amplitude was cut down a little bit, but it may not be enough. Okay. So when we design the trenches, like this kind of semicircular trenches, probably we should assume that those areas are not really effectively controlled. Okay. So based on this one, let me go step-by-step design procedures. Okay. For completely closed trenches, that means the area is 360 degrees. He also said, okay, minimum h over lambda r, minimum depth of the trench is 0.6 is required to have ARF less than 0.25. Again, how come he came up with this number? From his experimental result. And for theta is 90 degrees to 360 degrees, minimum h over lambda r was 0.6 is required. Okay. But required to have ARF less than 0.25, but it is only effective only middle region. Okay, middle region, I mean something like here. Okay. Again, middle region means only here. And for theta is less than 90 degrees, less than a quarter circle, then his conclusion, his findings were trenches are not an effective technique. Just installing the short trenches will not work.
Yes.
Ah! Do we have our cell phone policy in this class?
Yeah.
I don't know who this guy is. Maybe he's not Gareth. Let me check it that he's Gareth.
JR. Is-
How can we see the number? Let's select.
JR.
662 is from my home. I cannot blame Gareth. Ah.
Or you can just let us out of class early. Senior class.
Huh? You never heard of Korean song, right?
Not that I know of.
How come my wife called me? Oh man. Yeah. I will sing. Just a short piece of my favorite song. 꽃 피는 동백섬에 오 미와 끝 Then much.
At least there are only 4 of us.
Ah,
Camera.
No, it's going to millions on YouTube. That's the only way I can get the video to Gareth.
ah, I got to turn it off. I don't want to see it again.
I'm glad mine was on sound.
Yeah.
Yeah.
Ah, okay.
I made my ears hurt. Now you're seeing it was me laughing.
Sounded good.
Oh, wait. Get a note. Phone will
Now we
not.
only have a few minutes left. Do we want to make this leap into design or wait?
Wait a minute. Let me check. What is the next one? Let me see whether this one
I can see if that'll work.
may be better to be.
Open cell phone. That price for that cubic foot.
What's the
This one is for active
So, yeah, I need no depth, and I think I need no-
isolation.
No.
Again, when we design the vibration isolation, there is the 2 different techniques. One is the active, one is the passive one. This one is the active one, and there is the passive technique, and we will talk about the passive technique in the next class.
All we have is 8 minutes left on the recorder.
Okay, then I will close my lecture at this moment a little bit early. Okay, for the, I guess you guys have some homework to do today.
No.
No.
You've been slacking.
Shh.
It's on.
Yeah, because we were supposed to read that
It's all right,
paper,
though.
but then we came to your office last time, you couldn't find it. Supposed to read it today. You've been off your game today, Dr. Song.
Okay, I will check that the readout materials again, and we'll bring it to the Thursday.
That's your
class.
homework. Once you get that homework done, then you can assign us homework.
Okay. This one is for Garrett. You want to take Garrett one?
Yeah.
Yeah.
I
I'll
don't know
put that right to him.
what's the point of giving out.
Here we go,
the-
Garrett.
Yeah.
All right, page 1.
I will assign the homework next class.
Oh, he'll never be able to do that. Page 2.
We just scanned it, you know.
Yeah, I guess
It's too much work.
Page 3. Can you zoom in on YouTube? I don't even know.
I don't know.
Page 4.
I don't think so.
Yeah. 5. We've got 4 minutes left. 3 minutes. 6. How many pages is this thing?
Just like 2 more after.
All right.
Second to last one. Here's the last one.
Da, 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 da. Okay.